Okay, let's discuss these readings before going on to pre-lab, which again is a pretty brief pre-lab. So the first two questions here were in the opening parts of the text, but they weren't really defined at that part. So I thought it was important to go ahead and talk about them and hopefully get you to look them up and see what it is. First one says the text states that wavefronts are surfaces of constant phase. What does phase mean in that context?
Changing.
No. And I'm not sure anyone, some people got very more or less the right idea, so that I think that they understood what it was. If we've got a point source of waves, so that could be light or sound or whatever, any water waves, think of dropping a pebble into a pond and watching the ripples go out as rings. Those waves are all in the same phase. So they keep going out. So let's say that you take two individual photons that are traveling here. Photon 1, let's see if I can draw it. No, not like that anyway. Let's consider two photons going like this. Phase refers to what part of the wave are you looking at? So are you looking at a peak or trough? Either of those are important. Are you looking at a null? And saying two things are in phase means that two different waves, almost got it, are sharing those locations. So that at the same distance from the source, they have a maximum. That's what the phase refers to. So when we're talking about a lot of these, we're assuming what are called plane waves. We're far enough out that the waves are basically in a single plane. They're not curved anymore. And that they're also traveling in phase in a lot of cases. This isn't important for everything that we do. But that's what they were referring to. What part of the wave are we looking at, and are they together? If they're together, then they're in phase with each other. How do we say that letter?
Lambda.
Lambda, yeah. With the silent E. That's what's usually used for wavelength. I think even chemists use that. There's some difference between frequency is different letters depending on whether you're in physics or chemistry or whatever, but everybody uses lambda for wavelength. How are rays related to traveling light waves they represent? So they point in the direction of travel. What else? One other important part. Alex?
They're perpendicular to the wavefront.
Bingo. So those two things are the important parts. So if we have our point source of light again here, and we've got the waves going out, at some point these look basically perpendicular, but the ray is perpendicular, so straight out from that, perpendicular to our wavefront at that point, and showing the direction that it's moving. So something like this, you could have multiple rays going out. They'd all be perpendicular to the wavefront at this point and showing the direction of movement. They don't show the speed, although since we're talking light, all of these different forms of light are going to have the same speed. That those of you from last year are probably very familiar with. 3.00 times 10 to the 8 meters per second. And radio waves and microwaves and every other kind of electromagnetic wave travels the same thing. But next week, later this week, we are going to start talking about when light doesn't travel that speed and what happens. Law of reflection, I think everyone had, we did that in the lab, that the incident ray and the reflected ray and the normal line are all in a plane, and that the incident angle equals the reflected angle. What about wood and paper makes them colossal failures as mirrors? Some noted this really, really well. Others had parts. What's that? It's not, although it looks really flat, it's not. And why does the fact that microscopically it's bumpy make that difference?
Because then when the light hits it at a whole bunch of different angles. So
Right.
It bounces off kind of randomly.
Willy-nilly,
Yeah.
I think is the technical term. Right, it's called diffuse. Several people had that term, called diffuse light. So it's bouncing, rays are coming in this way and they're bouncing every which way, so that you don't get them bouncing off altogether, which is what's required to form an image, either a virtual or a real image. To be clear though, this is reflecting the light, right? That's why it looks white. That's why we can see it. It's reflecting light. It's just the fact that the white light hitting it is scattering in so many different directions that we can't see the stuff that light was bouncing off of. Okay, everybody understood this. Wording was different on some. If you stand 1 meter in front of a mirror and gaze lovingly into it, your image will be 1 mirror behind that, and as Candy noted, too far away to hug.
Just out of reach.
And differences, as we've all observed, between you and your image on that plane mirror will be that you are reversed left to right, but everything else is appropriate. The size, color, the distance there, all of those are appropriate. You're upright. So those are the things we're going to be looking at a lot with images formed in mirrors and in lenses, including today's. Is the image upright or is it flipped? Is the image magnified, which means bigger or smaller? And is it flipped left to right, so is it reversed that way? And on a plane mirror, it's upright. It's so upright. So the upside is correct. The opposite is upside down. Okay, explain what happens with light rays that makes it so they often seem. Wow, I should rewrite that question. I'll just read it as written. Explain what happens with light rays that makes it so often seem that an image is behind a mirror. Congratulations for anyone who correctly deciphered that. Despite the fact that the mirror is opaque and you can't see through it. And lots of people had various parts of this right. I think the best answers were the ones that said that although the light rays bouncing off the mirrors are diverging, they seem to, if you follow a line back, meet at a point and originate at a point behind the mirror. That was a very good answer on that. Okay. Any questions on the reading for those plane mirrors or what we did earlier, rays and things? While you guys are working on lab, I am going to set up that experiment that we talked about yesterday, trying to see exactly what shape a round beam striking the angled mirrors will make. But we're going to get started on our second lab. Which is called Mirror Images. You'll be using 2 mirrors, actually 3 mirrors. I've got to still find my flexible ones. I think they're right on top there. But you need 2 other curved mirrors, one convex, so that you'd be looking at a reflective side that bulges out towards you, and one concave, so that it goes in away from you. I've got several of each, so that you could form up in small pairs, or in small groups, but be kind, because there aren't so many that everyone could have one, unfortunately. And then I will also find some plastic mirrors that are flexible, that are right inside there.